What you're looking at, a somewhat complicated diagram that you and I are going to build up in this video, is a visualization unpacking the meaning behind one of the most powerful tools used to study differential equations. It's known as the Laplace Transform. This is one of those tools where, as a student, you can learn how to use it to solve equations, and yet be left completely in the dark about what it's actually doing. Think about learning how to drive a car versus learning how an internal combustion engine works. Both are worthy pursuits. One is not necessarily better than the other, and in fact, driving is probably more practical. But there is something deeply satisfying about popping open the hood and understanding the mechanism inside. Similarly, our main goal with this video is to pop the hood and show you some of the beautiful math that awaits us inside this object. And strictly speaking, a lot of what I want to show is not necessary if your only goal is to solve equations. That said, for the differential equation students among you, I think the content here should make the stuff you have to memorize a lot more memorable, and after dissecting this machine, studying it piece by piece, you and I will take everything for a test drive and see what it looks like to solve a concrete and very interesting differential equation. Now before I just plop down the definition on the screen, let's talk about what problem the Laplace transform is trying to solve. We set up a lot of this in the previous chapter, and there are two primary ideas worth restating here. Number one, you need to understand exponential functions, and I'm always going to be writing these as e to the s times t. T represents time, and then s is a number. It determines what specific exponential we're talking about, but very importantly for this topic, we're going to give s the freedom to take on complex number values. We covered this much more thoroughly in the previous chapter, but the quick summary is that if s has an imaginary part, the output of your function rotates in the complex plane as time ticks forward. When the real part of s is negative, the magnitude is decaying towards zero over time, but if it happened to be positive, that would mean the magnitude grows, namely growing exponentially. If any of that feels shaky, or if you want to understand why it's true, do watch the previous chapter, but from this point forward, I'm assuming everybody is comfortable with this notion. Why do we care though? Why the hubbub about these functions? Well, it's because of the second thing you need to know, which is that a lot of functions, especially those arising in physics, can be expressed as combinations of exponential pieces. There's one very friendly example that's going to be helpful to return to repeatedly throughout this lesson, the cosine of t. This undulating function can be broken up as a sum of two purely imaginary exponentials. Basically, if you take e to the I times t, that gives you rotation counterclockwise, and e to the negative it rotates the other way. So when you add these two together, perhaps imagining adding two rotating vectors tip to tail, the imaginary parts cancel each other out, and what you're left with is something whose output remains locked to the real number line, oscillating back and forth. Now as it stands, this sum goes between -2 and +2, but a cosine only goes between -1 and 1, so finally you multiply everything by 1/2. More complicated functions might break down into more exponential pieces. For example, later in this lesson, you and I are going to dig into something called the driven harmonic oscillator, which is basically a mass on a spring that's influenced by some external force, in our case one that oscillates over time. As a spoiler, the solution to the equation describing that ends up looking like a sum of 4 exponential pieces. 2 of those pieces oscillate and decay in a way that matches the natural resonant frequency of the spring, and then the other 2 oscillate in a way that matches the external force. So for cases like this and many others, what we would like is some sort of tool, some sort of mathematical machine where you can pump in a function, or even a differential equation describing that function, and that machine will somehow reveal for us what specific exponential pieces that function breaks down into. That is, it exposes what these values s in the exponent all are, as well as what the corresponding coefficients are. Now you might be wondering, why exponential pieces? Why not focus on something else? The short answer is that for these functions, when you take a derivative, it looks precisely the same as multiplying by some number, namely s. What you'll see by the end is how this means that same machine that lets us dissect functions into exponential pieces also allows us to turn differential equations into algebra. Essentially, because everywhere you see a derivative, it turns into multiplication by s. Now, in a context like this one, where we are so focused on complex valued exponentials, engineers have a special name for this complex plane that I'm depicting on the left, representing all possible values for that term s in the exponent. They call it, well, the s-plane. A helpful mental image is to think of each individual point on the s-plane as encoding the entire exponential function e to the s times t. For this picture, the graphs I'm showing only depict the real component of the output, but keep in mind, each point is representing the full complex valued function. These graphs are enough for intuition, though. You'll notice how bigger imaginary parts correspond to faster oscillation, and then as your eyes scan from left to right, the real part reflects either decay or growth. So with this as our goal, the machine that you and I are going to build up today, the one that exposes how a function breaks into exponential pieces, is, as you have no doubt guessed, the Laplace transform. Now this word transform is a little funny. Basically, in the same way that a function is something that takes in a number and spits out a new number, we often use the word transform in math for a more meta operation that takes in an entire function and spits out a new function. In the case of the Laplace transform, a typical convention is to name our new function with a capitalized version of whatever you use to name that original function. And in this setting, where our original function takes in time as an input, the new transformed function has a new different kind of input, a complex value, s. I think it's helpful to quickly preview what this new function actually does before we pull up the definition and start dissecting it. Suppose your original function, little f of t, really can be broken down as a sum of several exponential pieces. When you apply this Laplace transform, giving you a new function of this new variable s, if you were to plot this new function over the s-plane, in a way that I will explain in just a minute, what you see are these sharp spikes above each value of s that corresponds to one of those exponential pieces. These spikes have a fancy name. They are called the poles of your function. So even if you didn't know ahead of time how your function could be broken down as a sum of exponentials, if you understand this transformed version, and specifically if you understand the poles, that can reveal for you what those exponential pieces are. At this point, you're probably itching to see how this thing is actually defined, and in its full glory, this is what that definition looks like, which we can think of as two separate steps. First, you multiply your function by the expression e to the negative st, and then second, you integrate that result over time from t equals 0 to infinity. We'll talk all about that integral and its nuances in just a minute, but for the moment, focus on that inner expression. This term, s, is the newly introduced parameter, the one that is the input of our new transformed function. As I said, it's a complex number. Every time you see the letter s in this video, it's a complex number. And the way I like to think about it is that you might imagine freely moving around this value s on the s-plane, and it's kind of sniffing around to find which specific exponential functions line up closely with our function little f of t. For example, let's suppose our function is the cosine of t, which, as we discussed just a minute ago, we already know can be broken down as a sum of two exponentials, e to the it and e to the negative it. I've already previewed the idea that when you plot the final result, you should see these spikes over the key values of s, which in this example would mean poles above plus I and negative I. And you can already get a little intuition by taking this example and substituting in the expanded expression for the cosine of t. Looking at this expansion, I want you to take a moment to think about the product of these two terms. When you multiply two exponentials, the contents of those exponents add together, so what you're left with is e raised to the I minus s times t. Let me go ahead and plot that value on the lower right, keeping the s-plane on the upper right. Just like the exponentials we've already seen, as time goes from 0 to infinity, this oscillates and decays, or maybe it grows. The specific shape depends on how we set that value s. Now in this case, as you move around that value s, there is one specific value causing uniquely boring behavior. If you set s equal to I, then that term in the exponent becomes 0, so the entire function just looks like e to the 0, which is stuck at the constant 1. And this is a key idea. For almost all values of s, an exponential like this is going to change with time, typically looking like some kind of spiral, but at the special value that we're hunting for, in this case, s equals I, instead things get stuck at a constant. So, stepping back, if you were a mathematician and you're trying to invent some kind of machine that will detect the exponential pieces lurking inside a function, for example, detecting that a cosine has an e to the it and an e to the negative it lurking inside it, you might ask yourself, is there something I can do that can detect when one of the terms in a sum like this is secretly just a constant? In essence, this is the role played by the integral that is wrapping everything up in the full definition, integrating as time goes from 0 to infinity. And on the one hand, if you're comfortable with calculus, you might be able to anticipate why this would result in some kind of sharp spike over the desired values of s. If you integrate a constant from 0 all the way up to infinity, it blows up.